what you are going to talk about in this conference.
Yeah, first let me say that I find this organization since many years, and it's finally with the institute that we made here, very positive for young people who come and meet the scientists. And I'm also glad that I can come every year that this organization takes place. My talk will be basically on what is called string theory and its predictions in particle physics. String theory is a theory that unifies two of the main discoveries of the last century, the general relativity of Einstein and quantum mechanics, which was a dream for many years in the past. And it seems that string theory provides a way to do it. However, we don't know if this theory is realized in nature. And my research and my talk will be to try to find definite predictions and how this theory could be manifested in nature. So in particular, I will discuss how string theory can address present problem of dark energy in that we know that is needed for the description of the universe, and in the past how it can address the problem of the theory of inflation.
Okay. Very good, thank you very much. Well, the next question is concerning the institute. Now we have, you have seen the buildings here. I mean, the old dream started to be realized. So you mentioned already a few things about what we are doing here. So the real question is, what is your impression? You know a lot because you have been always here, about the progress of this program. I mean, what is your impression?
Yeah, I think it will be very important to make a step from organizing just a series of workshops and schools during September, essentially, around September, to once there is an institute, you can create programs in which people can come for longer periods, can have office,
and create research locally. Yeah, this is the.
It will be also good for Greek students, for all the universities in Greece.
To bring also the students from other universities in Greece.
And it will be easier to bring also scientists from abroad. And
the final question, since we don't have enough time, you have seen we have many young researchers around. What will be your suggestion? Is our field still interesting? They should continue? And
I think our field, yeah, it's an exciting field. That exciting from the point of view of also of very young people, I mean, already at the level of the school, because it concerns the fundamental laws of nature that govern not only at the same time very small distances. We know that the atoms started from the ancient Greece, but also very large distances that creates the evolution of the universe. So there have been experimental results continuously.
From both sides.
From both sides. Sometimes come more from particle physics, from LHC a few years ago, or from cosmology. So the next step is the ingredient how to stabilize the Keller class module, like the volume, if you want, of the manifold, or the compactification manifold. For that, there was an old idea to use non-perturbative effects. In other words, Gaussian condensation in a hidden sector in some part of the deep brains, and this generates a potential. However, it was known already at that time, back in '85, that this Gaussian condensation superpotential, when it is stabilized, the minimum is at de Sitter, and supersymmetry is not broken. You go back to de Sitter space. So about 2003, there was a proposal to uplift the de Sitter vacuum, which has negative energy, to a positive energy by introducing anti-D3 brains. These anti-D3 brains have preserved opposite supersymmetry from the D brain, so supersymmetry is completely linear supersymmetry is broken. However, no linear supersymmetry, it is preserved because the D3 brains break spontaneously the half of the supersymmetries which are preserved by the D brains. So this was the idea, under the name of KKLT, which allowed to construct, to stabilize the moduli and construct the Sitter vacuum. However, have been criticized. There is actually an ongoing debate on the validity of this ingredient of anti-D3 brains in the full string theory. There was an alternative proposal by the group of Cambridge, Claudio Corianò collaborators, which is under the name of large volume scenario, which replaces the anti-D3 brains by D terms, D-term potential from the D brains. So, but still, it had to be combined with the Gaussian condensation superpotential, which is based on the effective field theory. And still, there was a question whether this Gaussian condensation can be fit within string theory, satisfying all the requirements. So the debate continued even in that direction. Of course, you could ask the question: why don't try to use perturbative stabilization? I was using perturbation theory. This has an old problem, which is pointed out a long time ago by Danny Cyber, which essentially says that if you try to minimize the potential by putting together two orders of perturbation theory, then this violates the expansion, because usually the vacuum that you will find will be strong coupling. So graphically, you have a potential which is run away for, let's say, this, the horizontal axis is the volume or the inverse coupling. So at infinity, it goes either to a decompactified theory or to weak coupling, to zero coupling. And the potential is run away like this. Every order in perturbation theory is like this. So if you put two orders perturbation theory together, you may generate a minimum, but this minimum will be, it's likely to be at a strong coupling, or at at volumes of the order of string size, which violates the perturbative expansion. So the question is that you can ask is whether this there is a way out, and the idea is to take it again from field theory and look at the possible exception using logarithmic corrections, which is essentially the implementation of the Coleman-Weber mechanism. So let me describe you the idea in field theory. Suppose that you start with lambda 5 to the 4 theory, you compute the scalar potential. There are logs. These logs are absorbed into the coupling, into the quartic coupling, and the potential looks like this. It's the power of the coupling 5 to the 4. Obviously, this minimum, you will find a minimum either at zero coupling, because it starts from. So that's my conclusions, the summary, that present a new mechanism of module stabilization based on perturbative corrections, which are the basic ingredients are the logarithmic corrections, which appear due to localized gravity kinetic terms that arise only in 4 dimensions, upon compactification in 4 dimensions. And this seems to be an explicit counterexample to the De Sitter-Swamplet conjecture is defined. And I can also do inflation, which I didn't have time here to discuss. Thank you.
The first is, could you give us the highlight of your talk here?
Well, my whole career is focused on theories which are different from Einstein's theory of general relativity. And today I talked about the so-called brain world models, in which we believe that we live on a slice, if you like, of space-time. And there are other dimensions which extend outside this slice and which we cannot detect, of course, up to now at least. It is very challenging to reproduce whatever we know about four-dimensional physics starting from such a framework. Sure. And particularly today I focused on how we can justify the existence of black hole solutions that we feel, that we now know that they populate the universe in the context of such a higher dimensional theory.
Very good. And the second question is, since you have been here several times, maybe even as a student or not?
I first came in 1992 when I was finishing my PhD.
Very
it was
good.
that
So
year.
you see, and now you are established scientist. What is your impression of what you are doing here, taking into account that now we have, started the reconstruction of the buildings? It's a real start, not verbally. I mean, I was looking to the last building, which is over there, you can see from here, which is more advanced. So what is your impression of what we are doing here?
This series of workshops, because it is really, you've done a wonderful work in gathering here many scientists from Greece and from the whole world actually. So it is always a very enjoyable experience coming to Corfu. I mean, by itself the place is wonderful, but also the group of people that we meet here, they are actually front-end researchers doing very important things, giving talks about the more recent study. Even the reviews, we always learn something from that, even if we don't work in the same area. And this is the thing that I particularly liked. I could have gone to a workshop which is very much focused on, let's say, gravity. But coming here, the most enjoyable thing is that you have to talk with people that don't work exactly. You meet people that work on your topics, but not only these people. And sometimes you get questions about very simple things that give you a totally different idea of your work. So this is something really enjoyable. I have experienced that, as I said, from a young student when I was getting a fellowship to come here, and I stayed there for 2.5 weeks, I think. So it was a much longer duration. Now, unfortunately, I can only manage to come for a few days, but even then it is really beneficial. Exactly, we have other restrictions, job and family restrictions. But I always urge my students actually to
yeah,
come
that's true,
to
that's
Corfu.
true. And I think the students benefit a lot from the interaction with the senior people. And given that we have so many young people around, as you were several years before, what will be your advice? Is a nice field to continue? Is exciting enough?
It is exciting. It is exciting. Well, I get this feeling from all undergraduate students when I teach to them about black holes and cosmology. They get so excited. They want to do their diploma essays with me, and it's well, it has to do with the whole universe, and also the universe. It's always a very inspiring thing to think about, and therefore I would say yes. If this is what you like to do, this particular scientific direction is really open. We need actually young people to work. The questions are really many, and we would need every possible help from young and motivated students who love physics and want to follow their dream and do a difference. So thank you very much, and I would like to thank the organizers for their kind invitation. And I'm going to change topic a bit, and I'm going to pose the question whether we can localize asymptotically ADS black hole solutions in brain world models. It is actually a very old and long-standing question in brain world models. And that's why I'm going to start with a broad introduction to the topic. I'm going to go back and give you some different perspectives that have been followed over the years. I call them the brain and the bulk perspectives. And finally, I'm going to present also some numerical solutions. The question here is to build an analytic solution, such as the one I described before. After the introduction, I'm going to give you our bulk and brain perspective, which aimed to produce eventually a Schwarzschild black hole on the brain. If I have time, I will show you that we can do the same, but having a Reissner-Nordstrom / de Sitter black hole on the brain. And of course, then I will ask the question, what is the price to pay for such a construction? This talk is based on two recent works. One was actually last December in collaboration with my PhD student, Theodoros Nakas at the University of Ioannina. And if I have time, I will discuss also a more recent work that appeared last May. So as we all know, in 1999, the Adel-Sundrum models were proposed. The basic ingredient is that our universe is a free brain, which is embedded in a 5-dimensional bulk, which is filled with a negative cosmological constant. This is the line element of the space-time, very simple, only a warp factor in front of the 4-dimensional line element, and K here is the ADS curvature scale. In the Adel-Sundrum 1 model, there were 2 brains introduced, an observable and a hidden brain. The focus was to resolve the hierarchy problem, as we know, and indeed it was shown that every mass scale on our brain is exponentially suppressed compared to the corresponding scale in the hidden, in the Planck brain. Of course, there was a fine-tuning. The self-energies of the 2 brains had to be fine-tuned, and moreover, the self-energy of our brain had to be negative. In the Adel-Sundrum 2 model, the brain with a negative tension was pushed to infinity, only the positive tension brain was retained, and that was assumed now to be our brain. Therefore, the 5th dimension was infinite-sized, but nevertheless it was shown that the zero-mode graviton is localized near our brain, thus restoring 4-dimensional gravity. And there was, there could be a difference between the effective gravitational scale and the fundamental gravity scale, but not very large, because otherwise we would have produced a new hierarchy. And of course, these models were studied intensively for particle physics and gravitational physics and cosmological physics. I'm going here to focus on one particular question, which is what happens with the black hole creation. Since matter is local, oh, no. Thank you very much. I'm sorry about the sound. Okay, so when we have matter localized on our brain, we expect that if this gravitational collapse is complete, then a black hole should be formed. But of course, because a black hole is a higher dimensional object, we expect it to span all space-like dimensions, but we would like its singularity to be localized on the brain, although its horizon could also extend in the bulk. Indeed, this black hole solution is localized, then we expect it to have a regular asymptotic form. For example, it could be Minkowski on the brain and anti-de Sitter in the bulk to retain the ADS character of the bulk space-time. Now, this task has proven to be more difficult than we thought. We tried to construct, or at least to discuss, to investigate what it takes to derive a 5-dimensional solution that describes a black hole in the bulk, but also gives a black hole on the brain. And of course, having all the useful aspects, just like a pancake-shaped horizon or an anti-de Sitter asymptotic behavior in the bulk. And our construction started from the radiosodrome line element. We use a coordinate transformation to write the same line element in a conformally invariant way with a conformal factor here, as it's quite usual in the literature. We also used spherical coordinates on the brane because we want to construct a spherically symmetric solution. And in terms of the new coordinate, things doesn't really change a lot. The brane was at y equals 0, now it's again at z equals 0, and the ADS asymptotic boundary was y goes to infinity at the beginning, now is z goes to infinity. We also introduced 5-dimensional spherical symmetry, not only spherical symmetry on the brane, but also in the bulk. So we replaced R and Z in terms of rho, which is the new radial coordinate in the bulk, and an angular coordinate chi ranging from 0 to pi. Then the 5-dimensional line element has this, again, particularly simple form, where of course d omega 3 is now the line element of the 3-dimensional sphere. This is the geometry. If that is our usual free brane, the t, theta, and phi coordinates, okay, R is this one, and Z was the old coordinate along the extra dimension, and now we replace this with rho and chi, a new angle. Now the brane is located at cosine chi equals 0 because, or chi equals pi over 2, so it is exactly here because this is the value for which Z vanishes, and this is the location of the brane. And the two sides of the brane, the positive and negative Z, now correspond to two particular regimes of the chi coordinate. Of course, the two sides of the space-time are identical. I wrote rho, it is given by this relation r squared plus z squared, and as we see, rho receives contributions both from r and z. Now this means that when I go on the brane where z equals 0, then rho becomes identical to r. Also, if I want to go to the ADS asymptotic boundary or to the boundary on the brane, to a large distance on the brane, I just put rho going to infinity. As a further and final point of our construction, inspired by the work by Chamberlain, Hawking, and Rell, we now replace the flat part in our metric with the Schwarzschild solution. That is now the line element inside, apart from the conformal factor in the front, where f of rho, it was just a choice of our own, it is 1 minus 2m over rho. Why? Because now if I take chi equals pi over 2, the conformal factor disappears, and I take, because rho is equal to r, I'm taking the Schwarzschild solution on the brane. So I have a black hole in the bulk, and I have a black hole on the brane. Let's investigate a bit more carefully what happens in the bulk, because also in the Chamberlain, Hawking, Rell, we thought that we produced a black hole, but it was a black string. For that, I need again to investigate the scalar invariant quantities, and here the simplest one is the Ricci scalar. You can see that I have a constant contribution, and then I'm having terms which are inversely proportional to powers of the radial coordinate, and obviously these become diverged, they become infinite when I go to rho equals 0. But rho equals 0 means that I must take z equals 0 and r equals 0. Therefore, I have only one point in this 5-dimensional bulk where there is an actual singularity, and that is on the brane, since I'm taking z equals 0, and at the location of the mass, since I'm going at the point r equals 0. Therefore, the singularity is indeed localized on the brane. There is no other singular point either on the brane or in the bulk, all the way to the ADS boundary. And here I'm showing a plot of r. As you can see far away, I'm going to an asymptotically ADS space-time. Here, when I go at y equals 0, which is the brane, and r equals 0, this is where r obviously diverges because we meet the black hole singularity. Where the horizon disappears. And that is the geometry of the horizon. Here is the free brane. You can see that it may extend as much as it wants, proportional to the mass of the black hole on the brane, but it is exponentially suppressed as we move away from the brane, and finally it decreases to 0. And of course, the singularity remains on the brane.
And let me go to the conclusions. So we constructed a 5-dimensional gravitational solution describing a black hole with a singularity strictly localized on the brain. The horizon has a pancake shape. We don't need to introduce anything on the brain in order to do the consistent embedding. The induced on the brain's Schwarzschild metric satisfies the effective field equation. We can do also the Reissner nodes from ADS construction in a very similar way, but the field theory interpretation is still lacking. We still need to find something which respects all the energy conditions on the brain, it gives ADS asymptotically, and somewhere in between, in the bulk, it radically changes its behavior. If you have any idea about the interpretation, please let me know. Thank you very much for your attention.
So the first is, could you tell us the highlight of the talk that you are going to give in simple way, because this is going to be outreach.
Yes, so I'm going to talk about black holes in theories that modify general relativity, in particular what they call scalar tensor, which is the most simpler way to go beyond general relativity by introducing one more degree of freedom. So I will discuss several solutions we have found in these theories, and also solutions which are not existing in general relativity, like regular black holes and even wormholes, solutions which are, we know that may exist, but they're not in general, they're problematic in general relativity. And they are important because they could provide real signatures saying that we have something different from general relativity.
So this will be differentiate from general relativity.
This is the scope or the aim of our work.
Very
yes.
good. You have been a few times here. So what is your impression of what we do in this institute?
I must say that my field is a bit away from the particle physics.
Yeah, but we do also gravity, as you know. The emphasis this year will be mostly in gravity, if you noticed, in the other works, of course. But,
in the other, yes, I was speaking about this precise one here. Now, I always love to come here because it's like for me, it was the first conference I ever went to. When I started my PhD, the first year.
That I don't remember. Yeah.
Yes, I knocked the door on Professor Trakas and I told him I'm a young student, I'm from France, I don't have no money. Could I come to the Corfu Institute? And they helped me, and I'm very indebted for that. So whenever I can come, I always come. And now, of course, it's a wonderful opportunity after 2 years of lockdown to be able to see my friends and discuss with them.
We were there enough to start on life. And the last question concerns the young people. There are so many young people, which shows that the future can be bright for the whole field in general, particle physics and general relativity. What you will advise these young people? Should they stay in the field? Is it exciting enough to keep them?
It's a hard one to answer because it's very difficult professional-wise.
Sure.
But I think that if you love something, then you should motivate yourself in doing, in educating yourself in this. If you have this opportunity, it's a great opportunity. Now, specifically for my field, I think it is the most exciting time for my field because since a few years, we have numerous observations of black holes, we have gravity waves, we have telescopes, radio telescopes, X-ray telescopes that tell you that are starting to tell us incredible things about our universe. And in the next 20 or 30 years, it will be a real exciting time. It will be similar to the LHC switching on for particle physics.
Yeah.
So, for my field, I think it's a really nice opportunity and time to go there. It's going to be very, very exciting. But in general, it is for highly motivated people. The subject of my talk is a bit like Panagiota, it's on black holes. I'm going to talk to you in a synthetic way about recent results we have obtained with my collaborators. This is how do I have a pointer? Oh, yes. Okay. Okay. So my collaborators here, there's a nice bunch of them. So Tim Anson, who is actually finishing his PhD in a few days, who has been working with Evgeny Babichev. They are my long-time collaborators from Orsay, especially Evgeny, who is Russian, and Tim, who is English and French. There is a bunch of Chileans, Olaf Barke and Miguel San Juan and Mokhtar Hussein, who are in Talca, in Chile. There is Antoine Leibel, who's now in postdoc in Lisbon. Nick Stergioulas, who is an astrophysicist in Thessaloniki. Marco Chrysostomi, who is in CISA, doing a postdoc there. And my also very long-time collaborator and old boss, Ruth Gregory, from used to be in Durham, now she's in King's. Okay, so why are we interested in particular about black holes right now? I think it's a really exciting time for black holes and compact objects because there is a multitude of observational data. You all know about gravitational waves, but also arrays of radio telescopes like the Event Horizon Telescope or the Gravity Interferometer, okay? And of course also X-ray telescopes and other observations that are bringing us, first of all, gravity waves of binaries. These binaries can have been even neutron stars. We have the 2017 that gravitational boundary that came a few years, which was a neutron star merger. Another very interesting 2019 gravitational wave binary, which combined a black hole which is about 20 times the mass of the sun, and another companion, a secondary as we say, which is at 259 solar masses, which is actually what astrophysicists call the mass gap. They believe, we have believed for a long time, that there wouldn't be compact stars, compact objects in between about two sun masses and 5 sun masses. Well, there are. And so this is one of the new things that have appeared. And this raises a lot of questions, because if this is a neutron star, for example, then it needs a very stiff equation of state, or it needs to be rotating very, very rapidly at a point where it could be, in principle, unstable. And so this raises a lot of questions, which in recent years, in the future years, we'll maybe be able to answer. Now, the Event Horizon Telescope, you know it well. You have this image of, for the first time, of the black hole M87, which is like 4 million times the mass of the sun, an enormous black hole. The Gravity Interferometer that looks at our Milky Way Sagittarius A star, where we believe that there is, we have very good reason to believe that there's a central black hole there. And not only that, but since 25 years, we're observing stars going around Sagittarius A. And this is like a bit like we observe the planets going around the sun, but now it's stars going around the black hole. So gravity can be even stronger, but it's a lot harder, of course. And we're starting to get the Eddington parameters for the motion of what is star S2, for example, orbiting this massive black hole, okay? So we will be obtaining orbit characteristics. We have the mass for the moment, but angular momentum, and other characteristics, I will come back to that. And in future years, we will be able to see, to test the Noether theorem and things like that, okay? And the X-ray telescope, which is observing basically wants to observe what the equation of state for neutron stars is by looking at time observations of pulsars. Okay. Now, there are even more exciting things to do. Astrophysicists are very hard looking for pulsars that may be close to the black hole, because then this would be an enormous laboratory for strong gravity, enormous laboratory with time delay experiments. Okay. So this is a very exciting time to look at black holes. And in particular, you want to look at black holes that go beyond GR in order to have some measurable ruler of how you go beyond GR. If you are beyond GR or if you're not and you're just in GR. Okay. So here we find alternatives to GR black holes as precise rulers of departure from general relativity. Okay. This is our aim in our theoretical research. So in my plan, I want to start just reviewing GR black holes. Okay, then we will move on to scalar tensor. I won't spend too much time on the scalar tensor theory because it's just an effective field theory. I will tell you what I think is important about it and what is not. We will encounter keywords like stealth solutions, and we will use Brandon Carter's work on Kerr geodesics, for example, to create solutions in scalar tensor theories. So what I'm trying to say here is that what we learned from GR since a number of years is extremely useful even to go beyond GR. Okay, we will use methods which have been used in GR. For example, Gibbons and Pope used them Kerr-Child method in order to find generalizations of Kerr in higher dimensions very recently. And also we will use deformant transformations, which will permit us, I will explain what these things are, to even create exotic solutions like regular black holes. Okay. Tomorrow, Thanasis Barkopoulos is going to talk about wormholes even. And also create, solutions which are stationary black holes, which are not the Kerr black hole, which go beyond the Kerr black hole. We will get this analytically. We will have them the real metrics, okay, not numerically. So this is the aim. This is the idea of what we want to do here. So when I go on to scalar tensor theories, the interesting thing about them is that they are the simplest modified gravity theory with a single scalar degree of freedom. It's as simple as we can get, all right? And the other interesting thing is that scalar tensor theories, and I think that it's not that there's some fundamental theory, but they are a limit of most modified gravity theories. So if I think about, Panagiota talked about the Randall-Sandra model or the DGP brain world model, at some limit you can have a single scalar there. Or Ignatios talked to us about effective field theories in string theory, where you also have a multitude of scalars. Okay, so or if you take bigravity or massive gravity, there is a limit where you have a scalar tensor theory. Even if you start changing and you start inputting torsion or non-metricity, you can see it sometimes. One of the extra degrees of freedom comes out on top, which is a scalar degree of freedom. So in what I want to say by that, there's nothing fundamental about scalar tensor theories, but it's nice because in scalar tensor theories, we know in 4 dimensions what is the most general one, okay? And it is what they called DOS theory. We started with Brans-Dicke or Kordensky, beyond, and then DOS theory, which is parameterized by 6 functions of the scalar field and the kinetic energy of the scalar field, which is given here. And I just want to picture this. You see, you have higher order operators, okay? And the point is that you want to look at these theories because Brans-Dicke theory, due to no-hair theorems, only have the GR black hole solutions because there the scalar has to be trivial. Otherwise, the solutions are singular, okay? So what about these relations in these DOS theories between them? So Kordensky, beyond Kordensky, DOS. And what do you get? Well, So I do this formal transformation, which is not so difficult because x is constant, so d of x is just some constant. D is some like deformation parameter. And indeed, it is a deformation, it is a real deformation of Kerr. This metric that you see here can never be Kerr except if d is equal to 0. And why? Because it's very easy to check that for d different from 0, this is not an Einstein metric. So it cannot be a GR solution. So now you have this stationary metric, we don't know if it's a black hole, okay, which has been created by this formal transformation of the geodesics that we have used, which are regular everywhere, which is a solution of Dost theory and is a real different solution from Kerr. So this is, now is it a rotating black hole? So for each d, we have a new stationary solution. So you can think of it, this parameter d, you have to be careful because for each d, I go to a different theory. It's a theory parameter. But I can think of it phenomenologically as d being this formability parameter taking me to a different black hole, which is other than Kerr, okay? So in the absence of rotation, I explained to you before, like for Schwarzschild, it's just a coordinate transformation. But when the metric is rotating, the metric is not an Einstein metric. Now, the metric that I showed you before has a ring singularity like Kerr. It has an ergo region like Kerr. It is a causal spacetime, okay, which you can prove using a theorem in Wald's book. And it has an event horizon, so it is really a black hole. However, it's not so simple because the horizon in this disformed Kerr metric is not a constant r, it's a r equal to r theta surface. And as a result, the event horizon is not the killing horizon in this case, because you don't have the GR usual theorems anymore. And stationary observers cease to exist before hitting the event horizon, okay? So there is a region, there's a little sandwich, where your stationary observers will be space-like, but there will be directions in r and theta where you will still be able to be time-like. Last part space-time is not circular, okay? And this is because this dTdr term here, which you cannot gauge away. The physics are not integrable. But asymptotically, we have something which is very close to Kerr. You have higher order corrections, of course, and you can go and calculate the Pn parameters we did in the last paper. And we see, for example, that for whenever d is different from 0, you don't have the no-hair theorem that I was telling you about. So if you could measure Q, J, and M independently, and the no-hair theorem equation was not valid, then you would be in such a case. Okay, and now I'm finished. So this is, we have seen how to construct non-trivial scalar tensor black holes, which are well behaved, okay? We used classical results from GR and mathematical symmetries in order to construct many phenomenologically interesting solutions that can be used like D. You see, if D is different from 0, it's really like a ruler. Can I go away from Kerr, and how much can I go away from Kerr? Okay? We can even construct exotic solutions like regular black holes coming really from an action where the mass of the black hole has nothing to do with the coupling constants of the action. Okay? And Thanasis Bakopoulos tomorrow will talk to you about a wormhole construction in these theories. Okay? So, for the moment, gravitational waves, the Einstein Horizon Telescope, give certain constraints, like for instance for the light ring, for the coupling parameters. They basically tell us more about the mass than anything else, but there's a lot more to come in the future, and then we may or not see key differences with GR. And that's all. Thank you.
Yes.
So the first question is to give us the highlights of your talk yesterday.
Yeah, I mean, I try to convey the idea that in the early universe there should be some description. Matter interacts with gravity, and there should be in a phase that we call conformal. Basically, masses are not important. And then the question is how you to describe this this idea in a consistent way in quantum field theory. And for that we need to study some constraints, and that was the idea of the talk. And this has been going on also for some time. And there are a lot of problems, of course, which are still unresolved, which I hope we'll be able to push in the next the future.
Now, since you have been several times here and you have seen the developments and our tries and so on, you have seen the buildings that materialize now. Could you tell us, for the audience, of course, not for us, your impression of what we do here and the future?
What you do is very important, and international level, and connecting with the southern European countries, right? I mean, I come also from southern part of Europe. We connect these areas with the rest of Europe very successfully, and you have been doing it continuously, and it's very impressive what you have done in so many years. And the construction is going on, and it's clear we can see a lot of progress. Yes. So I hope that this will continue, and I hope that this school will stay here forever. I mean, so for the future generations, because it's an important.
And develop to other.
It's an important achievement,
fields,
I would say. Yes, it's not easy to do these things.
And we have all these young people, young researchers around. What will be your advice to them?
Well, if I can, I mean, I would say that one has to follow his own interest in physics, that's for sure. And in a sense, go also for uncharted territory, although it's a little bit risky, because sometimes we follow fashions, and I have never followed fashions. I follow my interest. Of course, keeping an eye on what's going on, and combining experiments with theory. So that's another important thing. Don't go just into abstract theory, and sometimes also not close your interest just into small things. Have kind of balanced view.
Okay, I think everything is smoothly setting up. So our speaker, as I said, our last but not least speaker will be Claudio Corianò. He will talk us about dimensional regularization and Gauss-Bonnet term and anomaly actions. Okay, thank you.
Okay, thank you for the invitation and for organizing this seminar, this conference workshop after COVID. Let's hope after COVID. We don't know whether it's over, but still. Okay, so I'll try to okay, so I will talk about some application of conformal field theory to the context both of ordinary conformal field theory in flat space-time, and I would say something about also curved space-time. And as you know, there are enormous implications of conformal field theory, conceptual level, in the context of string theory and critical phenomena and so on. And as you know, in two space-time dimension, the symmetry is very big, but gets reduced to 15 generators as you move to higher dimension. This analysis has taken several years, and we've been looking with my group on this topic, which is called anomaly-induced action. Essentially, as you know, conformal symmetry in even space-time dimension comes with the divergence. You regulate the divergence, you get an anomaly. And this structure has been known for a long time. Now the issue is what is the impact of these anomalies first in the context, of course, of flat spacetime, then curved spacetime. And there are significant implications, I think, which people are, at least we are starting, we start to study. And I will say something about cosmology. I won't say much because the work is still ongoing, but I will say more about flat space. So the point is that if you have a theory which is conformally symmetric, there are strong, from the point of view of quantum field theory, strong constraints on the correlation functions. These are constraints that people have studied in the past and can be easily, well, or more easily solved in coordinate space. But as you move to momentum space, there was basically no work done in the past. And so a few years ago, we started investigating the impact of conformal identities in curved space, in momentum space. And these results are collected in a series of papers that I've done with my students, also one with is obtained from the response of the Lagrangian of the standard model to variation of the metric. This is the standard way to define the energy momentum tensor, which it doesn't need, which is symmetric actually. But you have to keep in mind that there is a second term or a third term, if you want, in this interaction, which is what is called the term of improvement. This has to be introduced in order to have, let's say, a consistent theory. And the Higgs sector is conformally coupled. So the Higgs sector knows, or the renormalization of the standard model knows about the fact that the Higgs sector is conformally coupled. Otherwise, a renormalization, the standard model wouldn't be able to renormalize also this interaction with gravity. And so this is already significant information. Now, what is a linear level decoupling goes through fluctuation of the gravitational field. And this energy momentum tensor of the standard model is very complicated. To give you just one piece of it, just to give an idea of the complexity. And at least for the Higgs sector. So the Higgs sector contributes, you see here, to the stress energy tensor of the standard model. You can put all things together and compute. Now, what you find, just flash the result. For instance, if you compute one graviton to photon vertex, even in the spontaneously broken phase where you have mass of the fermions and so on, if you look at this vertex, there are some specific form factors which contain what this 1/s behavior. This is an anomaly pole. So what you get is why is jumping so much? Okay, that's fine. So what you realize, if you compute, for instance, the same correlation function, so one graviton, two gluons for QCD, you find a similar behavior as for the gravitational case. So you have a massive fermions, you find this 1/s behavior. And if you go and compute the entire contribution, you see that the residue of the pole is proportional to the beta function of the theory. So there is something specific which appears already in QCD in this type of correlation functions. Therefore, the contribution of the anomaly, this is a form factor which is responsible for the conformal anomaly. Basically, the trace of the energy momentum tensor of QCD in the process T into two gluons develops an anomalous trace. And this contribution can be generated by this non-local effective action where you have a beta function in front. So there is this interesting behavior which has been found originally perturbative by us, which is typical of the standard model, is always true. And there is a physical interpretation of this result. Basically, this has nothing to do in principle with gravity. This is just in flat space, but you can think of it as a graviton vertex in any case. But keep in mind that the stress energy tensor is and one interesting thing is that if you move away from the case in which from the Carroll case you give a mass, for instance, to your contributions to your virtual correction, you find this very interesting, beautiful behavior. Essentially, there is a sum rule hidden in these contributions, and this sum rules is essentially mass independent. What you find is that as you reach the conformal limit, the area of this of this region gets more and more squeezed until you get a delta function. So in other words, you start exchanging a pole as you go to the conformal limit. Now, I don't think this is trivial, and unifies both chiral and conformal anomalies. So there is a long story on this result that is contained in our previous papers. But let me go now and move on to new stuff. So there are two counterterms. Limit if alpha is a coupling, h mu nu is the variation of the Gauss bonnet term. You divide by d minus 4, you take the d equal 4 limit, they claim that you can evade basically the Lovelock theorem. So in other words, you have a theory of gravity, which they call Einstein-Gauss bonnet gravity, which doesn't contain anything else, and very less the Lovelock's theorem. Now, this is inconsistent, of course, has been shown by other physical regulators. People have written hundreds of papers on this thing. Now, I think we have a solution for this problem. And the solution is, I can just say it, although the paper is not out yet,